Right, guys, we're ready to crack Doppler.
Yes, we are. We are.
So let's get to that calculation and let's get the formulas out and make sure that we've got it all sorted out. So let's take our information. Remember, on your data sheet, you're going to be given the formula. Now, it's really important that you know this formula and you know how to work with it. We're going to say the frequency of the listener is equal to a number. I like to think of it as a multiplying constant. That constant can either be bigger than 1 or smaller than 1 times the frequency of the source. Now, guys, let's just stop there. Let's just treat this as a constant for the moment and say k. If k is greater than 1, then what can you say? Then you can say the frequency of the listener will be greater than the frequency of the source. Test it and check me. If this was bigger than 1, so it was 2, then 2 times fs, you can see it's going to be, fl is going to be twice the frequency of that. Even if it was 1,1, it would be bigger. But what happens if k is smaller, k is less than 1, then what are you going to do? You're multiplying by a number like half, then this answer is going to be smaller. Then what we're going to say is the frequency of the listener is less than the frequency of the source. Now I want to tie those two together. This happens when the object moves towards. We're going to get a bigger frequency. This means the frequency is bigger when it moves towards, and this one is it's going to be smaller. And that happens when the frequency is smaller when it moves away. And really, if you summarize that and you understand that, then you'll understand which formula to use. So we haven't got a k. We know we don't have a k. I was just using k there as a fraction. But what we do have is a fraction. We've got to deal with this fraction. So let's see what the actual fraction looks like. It looks a bit complicated, but you should be used to it by now. It's got this funny plus and minus sign all over it. Okay, so what are we dealing with? We're dealing with the velocity of sound. Have we got that? Yes, we've been given it, 340. We've got the velocity of the listener, the velocity of the source. Now, Indy, you were telling me that somebody was asking, can we do a problem where the listener and the object are moving?
Yes, yeah.
Okay, the source are moving. Guys, lucky for you, yes, you can use this formula. It does work. You'd have to wait to Physics 1 to do that. So for you guys in grade 12, don't worry. One of them will always be 0.
Yeah.
Isn't that cool?
Yes.
Okay. Now, they never used to have that requirement, but they do now. So you need to find out which one of them is 0. So we can simplify the formula straight away. We know that the frequency, the velocity of the listener is 0. But here's the trick. When you do this, you must substitute in all the values. So you must substitute in 0. So what have we got? We've got the frequency of the listener was 2080. So I'm going to substitute in now. I'm going to say 2080 is equal to, the velocity was given as 340 plus or minus, doesn't matter, 0. And now this is 340, and we don't know what the frequency of the source is. Guys, this is where you've got to start thinking. We know it's moving towards, so we want this fraction to be bigger than 1. So if we want the fraction to be bigger than 1, then we want the denominator to be smaller than the numerator. So the denominator, the thing at the bottom here, this part must be smaller than 340. Because if it was 340, it would be equal to 1. We want it to be smaller than 340 so that we'll get a fraction with something left over. So we're going to make that a minus. And we'll put that all in brackets and multiply that by the frequency of the source, which was 2000. 2000. It wasn't 2080, just 2000. Okay, and I'll put that in brackets so people don't get upset. Is that cool?
That's very cool. We actually have a few questions, and it's the same question from
Yeah.
quite a few learners. On Twitter, I think it's from Daryl Zulu, and then
Yes.
on Facebook, it's from Renata and Brian. But basically what they want to know is, let me have a look here. Basically, the Doppler effect question include like if simultaneous calculations.
Okay. We haven't got simultaneous
Okay.
here.
Yeah.
But we can do a simultaneous if we've got time.
Okay.
Straight after this.
Okay.
We'll just try and put one
Okay,
together
let's see if we
quickly.
have time. And then,
Okay.
yeah.
So it can come up. It's not a guarantee, guys, that it will come up. What you'll have to do there is a before and after scenario, and that's where they ask you. But really, it's not physics. It's really just some mathematical substitutions. If you understand the physics, you'll be fine. Okay. So now if we do the substitution here, then what we'll find, and I just quickly I'm going to do the algebra. I'm going to say that was 70720. What I've done is I've multiplied both sides by 340 minus VS minus 2080 VS, and I'm going to say, guys, that's equal to this value, 680000. Now, if you add, if you subtract 700 from both sides, you can get minus 2080 VS is equal to minus 27200, and we then divide, the minuses cancel out, and we get 1308 meters per second to the minus 1. Okay, so there you go. I hope you can see that would be a way of doing a simple Doppler equation question. There are other ways of doing it, and we've done this before. We've done it in a different way, where we've done a sign convention. I prefer this way because it makes you to think, but if you know the sign convention and you're going to say the direction from the observer to the source is always the positive direction, then you substitute into the values and it always does work. Okay.
Okay, I've got a quick question from Megan. It's got to do with what you're talking about, and it's quite interesting, I think. When substituting 0 for the object at rest, we were told to rather leave the 0 out completely, otherwise we lose a mark. Which way is acceptable for this exam?
Okay, as far as I know, you need to do substitutions for every unknown value. So you need to make sure that you do substitute the 0 value in, so that you can show the examiner, yes, you understand that the velocity of the observer in this case could be the velocity of the source in another example, but it is 0. Okay.
Okay. Awesome.
Okay. Now let's just quickly do one little section or little problem, but I'm doing this off the top of my head, so let's just make sure that we've got it right. What we're going to do is we're going to take a look at that question that we were being asked about simultaneous equations, and just to show you how you would do it and how you would sort it out. So here we go. Here's a particular example. Let's say that we've got a stationary observer, so we're going to say the observer is 0 and they're stationary. So we're going to give them 0 meters per second. Let's say if we've got the source over here, and we're going to say the source is moving with a certain velocity, constant velocity of, let's say, 20 meters per second. And what we are told is that the frequency of the source is unknown. The frequency of the listener when it's moving towards, let's just say it's something like 2000. We're not actually going to work this out. And when it moves away, then it's going to get less. So let's make it 1980. So frequency of the listener after. And what they then ask you to do is to find the frequency of the source. guys, what you've got to do for this sort of question is you've got to set up two equations, a before case and an after case, and then you solve them. So strictly what we would do is we'd say moving towards, and we would set it up with the equation when it's moving towards. We're going to say the frequency of the listener in this case is going to be, remember, we said make the listener stationary, V plus V listener, V minus V source, as we did just now. And what we're going to do here is we're going to say that we can then substitute. We can substitute the values for sound. Let's just take V as 340. And when you substitute 340 plus 0, 340 minus the constant velocity of 20 meters per second times the frequency of the source. Frequency of the listener was 2000. That gives you one equation. And the reason that it was minus here, because we know it's moving towards. So this value means that it's going to be 2000 is going to be greater than the frequency of the source. Now, as I said, I haven't worked this through, so I don't know whether it's a workable solution, but the second equation that you would set up would be when it's moving away. So let's do moving away. And what we'd have here is when it's moving away, we're going to say we know that the equation is going to be 180, let me just do it this way. Put that in first. And when it's moving away, we want it to be smaller. So we're going to say V plus VL over V plus VS, because now we want this part, the denominator, to be bigger than the numerator. And now I can do my substitution. So let me substitute now. And here we go. We're going to say that 340 plus 0 over 340 plus 20, it's constant velocity, and that would be your Vs. Now, what you've got is you've got perhaps even, you could then work out those missing variables. Take the two situations and you will be able to solve for the unknowns. I think what I've done is I've actually given you too much information, but set it out like that. What happens before, what happens after. You'll have two equations with two unknowns. Solve for one of them, substitute into them, and you'll get the answer. Okay, because this one, obviously, I've just seen it now. You could solve for Vs and you could solve for Vs, and it's probably going to be wrong because I just pulled it out of my head. It's not going to be the same answer. But I was just trying to illustrate a point. Okay.
Fantastic.
I hope that helps you guys.
Yeah.
Remember to set it up in those two parts. Label your parts. And then let's go to that. Are there any other questions on Doppler?
There are a few. I know we've got about 5 short minutes left.
5 short minutes. Let's see what we can do.
Let's start at the very beginning.
Okay, let's go.
Okay. Razia has said, but John, at my school they taught us to use both negative in the equation. And I think I did write back to her at the same time, so I'm not quite sure. Okay,
guys, again, let me just stress that to you, that it depends on the situation. Sometimes you will have one positive, one negative, but if one of them is 0, whether you subtract 0 or add 0, it doesn't matter. You're still doing the same thing to 0. So you're just showing that the 1 is 0. But what you need to make sure is when it's moving towards you, you're going to make sure that that fraction, because what we've done in both these cases is had the observer stationary. But remember, the source could be stationary. But you've still got to make sure that the fraction is either bigger or smaller than 1.
Okay, cool. Okay, are you ready for the next one?
Yeah, let's do it.
Okay. Sebolenkosi. I hope I got that right.
Yeah, of course, I missed it as well.
We're both doing it. Okay, so he wants to know, for the Doppler, if the listener and source are both moving in opposite directions, how do you calculate the frequency the listener hears?
You can't have them moving
at the same time.
Yes.
Okay.
So you can't do it. It's possible. to do it, but we don't need to do it for grade 12. You're writing grade 12 physics tomorrow, not university.
Yeah, and I mean, I just want to say, Alan Fizzy reckons he's going to crack tomorrow, thanks to us. So hopefully.
Good.
Yeah.
Guys, there's one last question we said we'd try and get back to, and that I think it was Malaji asked about threshold frequency and photoelectric effect.
Yes.
So I'm going to quickly just show you the photoelectric effect. And I'm not going to do the whole question. I just want to show you the picture. Radiation falls on an electroscope. This is a charged electroscope. If the radiation doesn't have enough energy, this electroscope will stay charged. But if it has more energy, has enough energy, this is what it's saying. Look here, ultraviolet light has, what happens is the leaves collapse. Okay? So if there's enough energy, ultraviolet lights, high energy, red light, low energy. Okay, and they go through a whole investigative question. Remember, it is important to know variables and all that sort of thing, and you need to know your practical investigative questions. But what I wanted to move on to is this. They're given the following information. The work function of zinc is that amount. The frequency of ultraviolet light is that, and the frequency of red light is that. They then ask you to define what the term work function is. I did this on Facebook, so you can see a more detailed explanation from yesterday's posting. The work function is equal to HF, where F is the threshold frequency. Now, threshold. Now, the threshold is the thing that you hit before you cross the door. It's that little step you go into the door. So you've got to get over the step before you can get into the room. That's what this threshold frequency is all about. It's the minimum energy you need to be able to kick electrons out of that photoelectric effect. So what I would define the photoelectric effect, or the work function, is it's the minimum energy required to kick out electrons. Okay, now last question that we're going to have time for today. Name one type of that is higher frequency than ultralights. X-rays would be higher, cosmic rays would be another. And here's the last question. It says, use a calculation to explain why red light fails to emit photoelectrons. What you've got to do is E equals HF. You substitute the frequency of light there. If they give you wavelength, then remember, then what you're going to do is you're going to say E is equal to HC over lambda. So depending on what they give you, use one of those two formulas, calculate the energy of that, and compare it to the work function. In this case, you'll find that the frequency of red light is less than the threshold, less than the work function, and so that's why it won't emit photoelectrons. I'm sorry, we did our best. We did. Covered big sections.
Yeah.
The last thing that I just wanted to mention, people were asking about projectile motion. Guys, if you need to make sure that you pick your direction, state your direction, and then you'll be fine.
Fantastic. And guys, good luck for tomorrow. We're sorry we couldn't get through everything. And please get onto the page and help each other out. And John is going to try his best.
I'm going to spend a little bit of time to give you some more answers.
But he's only one person.
Okay.
Yeah.
Help each other. We'll check your answers as well. We'll be on Facebook. So great to be with you. Thanks for being here, Indy. Please remember as well that we're here on Sunday afternoon. We're going to be doing paper 2 on Sunday, so we'll look forward to seeing you.
Yes.
Big thank you to everyone.
Thanks and good luck.
Good luck. Hold on.
Okay.
Bye-bye.
Bye.